Okay, let's take a look at your Lab 3. And see what you need to know to be able to figure this out. So, first of all, it tells you what a Mersenne number is. It's a number of the form 2 to the n minus 1. And a 4-bit Mersenne number detector needs 4 inputs labeled x3, x2, x1, x0, where x3 is the most significant bit and x0 is the least significant bit, and 1 output labeled Mer. Design any 2 of the 3 versions of a 4-bit Mersenne number detector using any gates available in the lab, using a multiplexer, or using a decoder. Those are your choices. So here is the way I interpret what it is that you are supposed to be doing. There we go. Okay, so first of all, what is a Mersenne number? So a Mersenne number is a number of the form 2 to the n minus 1. When n equals 1, this would give us 2 minus 1, which is 1. N equals 2, that would give us 4 minus 1, which is 3. N equals 3, that would give us 8 minus 1, which is 7. And n equals 4, that would be 16 minus 1, which is 15. And so you need to design a circuit that will detect if you have one of these numbers. And so in other words, it'll like maybe give you a light, the LED will light if it's one of those numbers and not if it's not one. And so your numbers are of the form x3, x2, x1, x0. And those are going to be your inputs. So you're going to have, those will probably be switches that you'll set. And you'll set them, and depending on how you set them, you have some output that would tell you whether or not it was a Mersenne number or not. So for example, let's say you had these attached to switches 3, 4, 3, 2, 1, and if you had them all turned on, then that would be the number 1111, which is 15, and you would expect that to say, yes, that is a Mersenne number. So your output would be, the light would be on. So your function would be on. So in other words, f of x3, x2, x1, x0 equals 1 when x3, x2, x1, x0 equals 0, 0, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 1, or 1, 1, 1, and it equals 0 otherwise. Because these are numbers 1, 3, 7, 15. So one way to do this problem is just to do a truth table, x3, x2, x1, x0. You don't actually need to do the whole thing out because we already know what it's going to look like. We have so you could design a regular circuit that just using regular gates to do that. So this is the sum of the min terms. So F is the sum of the min terms 1, 3, 7, 15. So if you wanted to, you could do a K-map. and so you could do a K-map. I think I did it wrong when I was in the session today, so it would be something to check on. It also depends entirely on how you set up your K-map. But you could also do it without a K-map just by looking at the numbers 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 1, 1, 1. So you can see if this is x3, x2, x1, and x0. Let's see. So you could have, if we look at this bottom two, x2, x1, x0, or x3 bar, x2 bar, x0. So on these this bottom group right here, these three are 1, all 1. So that's x2, x1, x0. And on this top group right here, we have x3 and x2 are 0, and x0 is 1. So that would be the function, and you would just need to implement that. So you could draw that. Or you could use a multiplexer. So let's take a look at what a multiplexer does, and the multiplexer that you can use. So here that's the demultiplexer. We want the multiplexer. The multiplexer is chip 74151. And you want to be careful and look at the truth tables for these. And so we have here we go, here's the truth table. And so we have an enable bit, and the enable bit has to be low, so that's ground. And then you have S2, S1, S0. Those are your select bits, so that will select the value that you want. And then you'll have your inputs I0, I1, I2, I3, I4, I5, and so forth. And you'll have your output based on that. So what you have is your multiplexer. And these values are I0, I1, I2, I3, I4, I5, I6, and I7, and you'll have an enable, but you will want to connect that to ground. And then remember, the way a multiplexer works is it looks at the select, and whatever binary number these select bits are, that's what the output is going to be. So for example, if x2, x1, x0 is 1, 0, 1, which is 5, then whatever is input into I5, say it's 1, that would be what the output is. And here in our On our chip it's called Z. And so these values determine what your output is going to be. So you want to look at the numbers you're trying to detect, and realize you can only use 3 bits, you can't use all 4 of them, and decide which 3 you want to use, and based on those 3, what inputs you want to have. So I'm going to do something different. This is not your project, but let's say you were trying to detect these numbers. Let's say you were trying to detect these numbers. Then you could pick 3 of these bits and have them be your input, and let's just have them be these. And so if this is what we had, then this is the number 5, 7, 0, and 4. So we would want to have a 1, a 0, 4, 5, and 7. And we'd want to have zeros everywhere else. And so what that would give us is it would detect for us that whenever we had this combination of bits. And then what we would want to do is we would want to have well, I'm going to change my example because this one just, the numbers don't work very well, so I'm going to change it to say these are my numbers. And that still gives me this. But then, with my output, the way I'm going to detect this last bit is I would take this and I would AND it with, if this is x3, x2, x1, x0, I would AND it with the NOT of x3. If those were my numbers, and then that would be my function. So that's how you could use a multiplexer. Now the way a decoder works, if we look at our decoder, somehow I'm not able to change the page. And so if we look at our decoder, we see how we have our inputs. Notice these have the least significant bit first. This has A2, A1, A0. And so if I'm looking for when X2, X1, X0 equals 6, that would be A2 equals 1, A1 equals 1, and A0 equals 0, and that would be written because they have the least significant bit first. So that would be low, high, high is equal to 6. So low, high, high is 6. And what it does is it outputs a value of low only on the output that corresponds to the binary number of your input. So for example, what are those eyes? I think they were. If I put in 0, 0, 0, this is going to be low here at the 0th one and high everywhere else. if I put in 0, 1, 1, that corresponds to 0, 1, 1, that corresponds to 3. I'll have a low only at the 3. And so the way you can use a decoder is if you look at these 3 bits, look at the last 3 bits, you could take the output for a 1 or a 3, so from your decoder one and 3, and that, so, or those, and then and that with x3 naught. Or these last two have just x7, so that would look like that. You also need to make sure that you look at how the enable bits are supposed to be set, and that you pay attention to the order of the inputs.